Okay, let's work on the second problem. So the second problem is going to be convenient if you have adopted the ICE table method, because we're going to start talking about how buffers change, and it's easiest to understand how to set up the problem if you've been using if you've been using ICE tables correctly up until this point, because it's fine to use the Henderson-Hasselbalch when you're at equilibrium, but when you start changing equilibrium, the ICE table is going to be what you need. So we're told to calculate the pH of a buffer from question 1 after we add this many moles of NaOH to the 1 liter solution, and we can assume no change in volume. So initially we started off with 0.3 moles of HF and 0.7 moles of fluoride and none of the H3O plus. That's not correct. Sorry, we just solved for that. 0.000304 moles, okay, because that came from the X above. And so initially this is what we have. It's what was at equilibrium before, and now we're going to add a strong base. And so the first thing we have to do is to determine what the base will do in this problem. So when we add a base, this is going to react with the HF, which will shift the reaction to the right. Okay, so it's going to, if we add HF plus NaOH, it's going to make more fluoride and more hydronium. Okay, and then the sodium's out there, but it's not necessarily partaking, it's a spectator, so we don't see it on the other side. Okay, so now that we know which direction the equation is going to shift, we know that it's going to shift to the right, which means it's going to consume the reactants and produce more products. And because it's in a 1-to-1 ratio, stoichiometrically, there's no, remember the change always has the stoichiometric factors involved. Now that's going to leave me at equilibrium with this total. Okay, but what I really don't, what I want to solve for is really what this value is going to be. Okay, so even though we're starting with this amount, we don't necessarily know it directly, if that makes sense. This is our unknown, and so now we can use the Henderson-Hasselbalch. And I could have written in the pKa value because it shouldn't change, so that's going to come down to be 3.15 plus the log of AHA, and the volume being 1 liter. It's nice because we don't have to worry about converting from moles to molarity. It's equivalent. And now we get to solve for the pH. So the pKa is 3.15, and now I'm going to take 0.278 or 0.78 divided by 0.22, take the log of that, 0.22, and that gives me that can't be right. Oh, there we go. I was doing something wrong. Okay, I'm doing this on my phone calculator, which would absolutely not recommend. Okay, which gives me a pH of 3.7. So you take the 0.78 divided by the 0.22, and then take the log of that, and that's where the 3.7 comes from. Okay, now I could have solved using the Ka that I'm given, and I could have done it the exact same way as I did before, where I don't know the value and then taken x and plugged it into the pH is equal to, and I should have gotten the same exact answer.